All right, so we will get started on today's worksheet. So today we're going to work on more chapter 9 stuff. Like I said, chapter 9 does not have near as much information, or I guess not as much material as some of the other chapters. So we're going to do one part of chapter 9, which is these molecular orbital structures. And then we're also going to do some review for the final, which you guys requested or said would be good yesterday. So are there any questions before we start on today's worksheet? All right, so if you could just put your Iowa State ID in the chat, I would appreciate it. And we're going to begin with discussing molecular orbital structures. And so these, the molecular orbital structures are the, if someone had a question, I didn't catch what it was. The molecular orbital structures, these are kind of like, what are they called? Orbital box diagrams. But rather than doing just for one atom, we're going to do it for molecules. And so there's a specific way you do this, and I'll draw it along with you. And then what we're going to want to determine is how many bonding electrons there are, how many anti-bonding electrons there are, and then what is the bond order, this one here. This is really the important thing. And so the bond order is like how many bonds are between the molecules. So like if we had a double bond, that means the bond order is 2. Triple bond, the bond order would be 3, and so on. So this is a way to predict the type of bond that will be between molecules, or between atoms in a molecule. So there's this structure, and I'm going to draw this with you, but you can take a picture if you want. So let's just go through what this structure is, and we're going to draw it together as well. So here we have the space on the left side for one atom. So notice here you have the 1s, the 2s, and the 2p. So in our case, we're doing fluorine. So this side is going to be the orbital diagram for one fluorine. And then on the right here, we have another space for a fluorine. So we have 1s, 2s, and 2p. So we're going to have another fluorine molecule over here. Now in the center, we have different energy levels. So here, this is the 1s. And here we have a sigma 1s. All right, yes, here is a sigma 1s and then a sigma 1s with a star, a little asterisk. And so these star ones, these are what we call the anti-bonding. I couldn't really tell you what that means, but the star always signifies an anti-bonding, and then the ones without the star are the regular bonding. So same thing here, we have the 2s level, so 2s here, and then we have a sigma, which is the regular 2s bonding, and then a sigma star 2s bonding. So these are the anti-bonding. We'll just say the star here equals anti-bonding. And then same thing up here, but up in the top level here, we have 2p. Now, once you get into p, it's a little bit more complex. So we have the sigma 2p and then a pi 2p. So if you remember when we were talking yesterday about the shapes of the p orbitals, they're more like dumbbells. And so in that you get pi bonds in addition to sigma. And then once again up here we have the star ones, which are the anti-bonding. So let's go through and do one of these for fluorine. And we're going to do it together. And these ones are always going to be the same. So the same, I mean, as in the same setup, right? So the same structure. So on one side, we're going to have a fluorine molecule and another fluorine molecule. And let's draw out to begin. Let's draw out together the different levels. So we have a 1s, a 2s, and then a 2p. And the 2p is going to have the 3 boxes. And on the right-hand side, we're going to do the same thing. So it's going to look like this. So 1s, 2s, and then 2p. Now, before we start putting everything in the middle, what I want you to do is take a minute or two and fill out the orbital diagrams here for both of the fluorines. And what I mean by that is just start putting in the arrows and stuff, okay? So why don't you take a minute or two to put those in for both of the fluorines. Oh yeah, sorry, Kristen, I'll scroll back over here. If you want to take a picture quick, we'll be doing this all together, but feel free to take a picture for now. I'll scroll back over to the left. All right, great. All right, so let's fill these in for fluorine. Now let's just review quickly from the periodic table how we get the number of arrows. So the fluorine is in, let's see if I erase a little bit of this stuff. Fluorine's over here, box number 9. Therefore, we have 9 arrows in each of the fluorines. So we're going to put those in. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And same thing on the right, we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have our arrows in, that's good. And so once we have our arrows put in, like our regular structure, we're going to start building the middle part. So let's do this together. So we're going to have the 1s level, or excuse me, the sigma 1s. And we're going to have the sigma 1s star. And then usually you connect these with like little dotted lines coming across the middle, just to signify that these are both coming out of the 1s. Then for the 2s, we're going to do the same thing. We're going to do a sigma 2s and sigma 2s star. And these you can kind of connect with dotted lines again. Kind of like that. And then the 2p, this is a little bit more complex. So once again, we're going to have the sigma 2p, and then we're going to have a pi 2p. And the pi 2p, so pi 2p is 2 boxes wide. And then once again, we're going to have the pi 2p star. So pi 2p star. And then a sigma 2p star. And I will try to just draw some more dotted lines here. So these are all coming out of the 2p. And it doesn't have to look perfect. I think usually they would have you draw like one of these on an exam, but I'm not quite sure what they're going to do this semester. They might just give you a picture and say which one is correct or which like structure here looks right. Now, before we start filling arrows in the middle, what questions do you have so far?
So
there's always going to be, oh, go ahead.
I was just going to ask, it'll always look like that in the middle, like to start with?
Yes, yes,
Okay.
it will always look like this in the middle. Good question, sir. Well,
And then there's always the anti-bonding. There always has to be one.
Yep, yeah, there's always going to be the anti-bonding. So anything you draw for the regular, you have to also draw a level for the anti.
What exactly are all these numbers, sigmas, pi's, like what?
Yeah, I know it's kind of confusing. So the sigma bonds are the bonds that are directly between the two atoms, and then the pi bonds are like the ones that are overlapping from above and below the atoms, like kind of like we discussed yesterday. And so what this is doing here, this is just a theoretical way to determine the type of bonding between the molecules. And I'll show you why we do the structure at the end. Really, we're trying to get the bond order. And I think it's a little tedious, in my opinion. So now what we do is we're going to move all of these arrows into the middle. And all we want to do is count up the total arrows on the left and the total arrows on the right. So we have 9 arrows here and 9 arrows here. And so just start filling them in from the bottom to the top. So just like this, so 1, 2, 3, 4, and so on, all the way up through the structure. So we should be putting a total of 18 arrows in. So why don't I give you maybe 30 seconds or so and just try to start putting in some arrows. Okay, so let's do this one together. And if you're still filling, just make sure you're filling them in the same way that I'm doing it. So we have 18 total arrows. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So following the same rules, 1 in each box before you put 2, and then just moving up the tower. So now we have our completed molecular orbital structure. Now, before we get on to determining the number of anti-bonding and regular bonding and the bond order, what questions do you have so far?
Why do the pi 2p's have 2 lines instead of just 1?
So actually, I'm not sure why. I know that the total number of electrons here plus here, or the total number of spaces here and here, have to add up to the total. So there's like 3 spaces here and 3 spaces here. So that's a total of 6 spaces. And right here in the middle, there's 6 spaces. I don't really know why there's 2 for the 2p. It's more just me following stuff from the book. Yeah, sorry if that's an unsatisfactory answer.
That's okay, thank you.
Yeah. So Francis asked, are there ever any D levels? I am sure there are. but they're never going to ask you for a D level. That would be brutal. At least I've never seen them ask on a D level. It's always something like this. So let's start counting the bonding, the regular bonding and anti-bonding. So we have the bonding. So the regular bonding electrons. See, we had another question here. Okay. So the regular bonding, all you want to do is count up the ones without the stars. So like this one, this one, this one, and this one. All of the arrows in those ones. And then the anti-bonding, what color I want to do that in? Do a purple. So the anti-bonding, you're going to do the same thing, but you're going to select all of the ones that are in the stars. So just add up all of the arrows in the stars and the regulars. And then once you have those, we can calculate the bond order, which is really what we want to go for here. So bond order is going to be equal to, oops. So the bond order is the bonding minus the anti-bonding divided by 2. So once again, add up all the bonding ones, which are the green circles, add up all the anti-bonding, which are the purple circles, subtract them and divide by 2. So I'll let you work on this for a couple minutes, but as you're getting started, what questions do you have?
So are we just counting the arrows then?
Yep, we're just counting arrows, Madeline. All right, so when I added up all the bonding ones, which were all the arrows and the green spots, I got that there were 10. And then the anti-bondings, I got that there were 8. So if you did the bond order, you would get 10 minus 8 divided by 2. And so that would give you the bond order is equal to 1. So all of that work and your answer is 1. So does anyone know what does the bond order mean, or could relate it to something that is more familiar to us? So Hannah said bond strength. Yeah, so if we were, so remember, we're doing a fluorine molecule. We did this structure. See right here, it says draw the molecular orbital structure for a fluorine molecule. So the bond order predicts that this fluorine will have a single bond between it. And so a great way you can check to see if you did this correctly is draw the Lewis structure and see if when you draw the Lewis structure, is there a single bond between here? that means the bond order is 1. So again, really a drawn out way, in my opinion, to get the bond order. But I guess it's something they like to test on in this class. So what questions do you have on anything from the molecular orbital structure?
So on the homework, I got a bond order of 2.5, and then it
Okay.
asked for like what bond it like represented or whatever. What would that be?
What were the multiple choice answers? Was it
There was,
multiple
like-
choice?
Yeah, it was like single bond, double bond, triple bond. And then like a single bond with a double bond with a triple bond, and then like
Yep.
no bond.
So great question. I can't quite see who's talking there. Oh, is that Kristen?
Yep.
So remember when we did some resonance structures? Oops, or I lose here. Let's say you had this structure, and I don't remember. Let's call it X and A. I don't remember what the atoms were. So let's say you had your resonance structure that was single bonds here, but a double bond here. Remember, the bond order can be calculated from the Lewis structures by adding up the total bonds divided by the bond locations. So we have 4 bonds and 3 atoms that are bonded. So 4 divided by 3 equals 1.33. Now, Kristen, what you have to do is take this number, this is what you found, but yours was 2.5, and you have to work backwards and think, what structure gives me a bond order of 2.5? Does that make sense or no?
Yeah, it does. Thank you.
Okay. Are there any other questions on this thing here?
How do we know what to do, like if the element's bigger than fluorine? Like how high do we go with this? With the sigma?
Well, so you could just keep slapping on levels. So the next section would be sigma 3p, pi 3p, and so on. I don't think they're going to ask you to go to D. You would have to look up what the D structure is, because I actually don't know. But I find it hard to believe that they would ask you to do anything higher than just the P levels.
Okay.
All right, so that's what I had for today for chapter 9 or whatever. So I had some stuff for reviewing for the final. So I think we're going to jump into this. So yeah, feel free to begin on this, and then let me know what questions you have as you're getting started, because I know this stuff was from like 3 months ago, and it might be kind of evasive. I'll just write down the formulas here for number 1 and 3, just so just in case anyone's lost and don't want you to have to flip through your notebook again. All right, let's begin looking at number 1. So the temperature ones, these ones aren't too bad. It's probably just remembering the formula. So I wrote down here, so it's 5/9, so 5 divided by 9 times Fahrenheit minus 32, so 105 minus 32, and then just put that in your calculator, and this comes out to 40.5 Celsius. And it's usually easiest to go all of these to Celsius, I've found. But if you want to go all to like Fahrenheit, you can do that too. And so this one, the formula is Kelvin minus 273. So that would be 299 Kelvin, which is the given temperature, minus 273. And that gives a temperature equals, put it down here, equals to 26 degrees Celsius. So from here you can see, since they're all the same temperature now, all in the same units, you can determine that this one, part B here, is the highest temperature. Okay, so moving on to number 2. Define and give an example of a physical and chemical change. So a physical change is, it means the chemical formula stays the same throughout the process. So for example, if you have H2O at the beginning, it's still H2O at the end. And then a chemical change is going to be a change in the chemical formula. So if you had, H2O and it changed into hydrogen and oxygen separate, that's a chemical change because it's a different chemical formula, it's a different species. Just color that, we'll do purple. So what are some examples of a physical and chemical change?
Would like physical change be like ice melting?
Yes, very good. That's a really good example. That's what I was going to say. So physical change, this would be melting. That's a really good one. Are there any other ones people can think of? So anything like boiling is another one. Freezing, anything like that. Freezing. That's another really common one. Any of the phase changes are super common physical changes. And then a chemical change. Does anyone have an example of a chemical change?
Burning.
All right, very good, Ben. Burning, that's a classic one. Does anyone have any other ones?
Rust forming.
Yes, rust formation, that's a good one, rust. Rusting. And then, let's see.
Color change.
Yeah, color change, that's another one. That's really good. I wouldn't have thought of that about that one. Yeah, so usually color changes are accompanied by some sort of a chemical reaction going on there. All right, so then, again, if you have any questions, feel free to just ask away as we're going. Number 3 is calculate the average atomic mass for magnesium using the following data. So the formula for these are, you have the percentage of one isotope times the mass plus the percent of the next one times its mass and so on. So you can just label if you want. You can say this one I'm going to call A, this I'm going to call B, and this I'm going to call C. So the average is going to be the percent of A, which is 79. And don't forget, we got to write this in decimal notation. So 0.7899 times its mass, which is given here 23.985. I'm just going to round a little bit just because I don't want to write so much. So these two numbers, we're going to multiply these ones. Then the second one, part B, which is 10%, says 0.100 times its mass, which is 24.985. About. Again, when I'm putting it in my calculator, I'd probably use the full numbers. And then the last one, 11%, 0.1101 times its mass, 25.98. So we're just stringing those all together and then putting in the calculator. And when you do that, you should get an average atomic mass of 24.305 atomic mass units. What questions do you have on anything from number 1 to number 3?
Could you have converted the ones in number 1 to Kelvin? Because I got that A was the highest one, and maybe I did it wrong.
Okay, so I will check on just a calculator to see what they're, but you can definitely change them all to Kelvin, Megan, if you want. So as we get started on the next ones, I'll run through and check that. All right. So I have a few on, let me just scoot these together a little bit more. From a few different chapters here. So we have a balanced equation, a percent composition, and then naming some polyatomic ions and their corresponding acids. So as you're beginning to look at these, I'm going to write down the equations, or the format you should follow, and let me know what questions you have as I'm beginning to write down the equations. By the way, Megan, I checked in, I got the same temperature as I did on the worksheet using just a Google calculator. So maybe you just made a small error somewhere.
Yeah. Okay. Thank you.
Yep. All right, let's begin looking at these here. So starting with number 4, I wrote out the equation for a combustion reaction. So remember, we have some sort of a fuel, and in this case, it's going to be the butane, so C4H10. And so this piece here, they're probably not going to give you. So you're expected to know that a combustion mixes with oxygen to produce carbon dioxide and water. So once again, I like to draw a little chart under here and count up the atoms on both sides. This always helps me. If this doesn't help you, then that's fine. You can use your method as well. So on the left side, we have 4 carbons, 10 hydrogens, 2 oxygens. On the right, we have 1 carbon, 2 hydrogens, and 3 oxygens. So what I like about this is you can easily see what you need on both sides. So we need four carbons on the right. So I'm going to put a 4 here. And that's going to increase the number of carbons up from 1 to 4. It also increases the oxygen. So this will be 8 plus 1. So that would be 9. So this we're going to cross off here, and this becomes 9. All right, so now we need more hydrogen. So I'm going to put a 5 in front of the hydrogen. And so that's going to give us 5 times 2 is 10 hydrogens. So hydrogens goes up to 10 to match what's on the left. Now we also increased the oxygen. So we have 5 oxygens here, and here we have 8. So that is, was that 13? Yeah, 13. All right, so now our last one is the oxygen, which is the simplest one. That's why I usually leave that for last. So we have 13 oxygens, and the problem is they come in pairs. So there's 2 of them here. So we have 13 oxygens, but they come in pairs. So what I like to do is divide by 2. Now you can go through and do kind of like an iterative solve for this, but just doing more and more, figuring out how many oxygens and hydrogen and carbon. But what I like about doing this way is there's a simple way to get rid of this fraction. So let me just explain again. We had 13 oxygens here. We want there to be 13 oxygens here, but since they come in pairs, it's O2, I divide the 13 by 2. Now, does anyone know how we can get rid of this fraction here?
You just have to multiply the whole thing by 2.
Yes, that's exactly right, Megan. So to get rid of this fraction, we're going to multiply everything here by 2. So we put a 2 here.
Yeah, Megan.
This goes to 13. This goes to 4 times 2. This is 8. And then this times by 2 goes to 10. So we're doubling everything across the board. And now if you look, we have, oh, what did I do 13 times? So this is, yeah, that's fine. So now our equation is balanced. What questions do you have on the balancing the equation for butane? All right. So number 5, what is the percent composition of nitrogen in this caffeine molecule? So the equation is the mass of all of the nitrogens. So in this molecule, we have 4 nitrogens, and each of them from the periodic table are 14.01 grams per mole. And the total molar mass for this molecule, so we're just going to add up the molar mass for the entire thing, and I get a total molar mass of 194.19 grams per mole. So I multiply 4 times the nitrogens, divide by the total mass, and that will give us, oh, and then can't forget times by 100, because this is a percentage, and that gives us 28.85% nitrogen. What questions do you have on number 5? All right, so let's talk about number 6. So this is going back almost all the way to the beginning of the semester and naming the polyatomic ions. Now, remember what we're doing with this is we're determining which of these is the quote unquote standard one. also known as the one with the ate ending, ATE. Now, who can tell me which one of these is the standard one and how they knew that?
Is it SO4
it-
2 minus?
Yes, it is. I think two people were about ready to say. So SO4 2 minus, and this is sulfate. And the way we know this is there's just a, where is it? Polyatomic ions. There's just a sheet of these. So if you don't have this, I would take a picture. And once again, looks like we did this one last time. It's just listed on here. This SO4 is sulfate. And so, you just have to have this list as, either in your brain or as a reference. So sulfate, now as we go up oxygens and down oxygens, we just change the prefix and suffix. So this would be per sulfate. So I'm adding the per on the beginning. For SO3, we're going to change ending to ite. So sulfite. So the ending changes to ite. And then SO2, which is another oxygen gone, we do hyposulfite. So hypo and ite. So these are all derivations of the standard one, which is sulfate. Now, if we were going to change these into acids, does anyone remember the naming rule for changing the polyatomic ions into acids? So the rule is ate ending goes to ic, and an ite ending goes to us, O-U-S. So if we were changing these to our acids, we just have to change the ending. So per sulfate would be per sulfuric. There's the ic ending, and then you just say acid at the end. For sulfate, so this would be sulfuric. So once again, adding the ic ending, ate goes to ic, acid. For sulfite, this would be sulfurous. With O-U-S, acid. And then for hyposulfite, this would be hyposulfurous. So the O-U-S, acid. What questions do you have on naming any of the polyatomic ions or their corresponding acids? All right, so feel free to hang out if you have any other questions. Otherwise, we will pick up on Monday's session at 4:30. Yeah, other than that, have a great weekend and see you next time.
Thanks, Matt. Love you.
You're welcome. See you, Ben.
Thank you.
See you, Megan. You're welcome.